plumbing science and some plumbing maths here. So let's work out heat energy required for hot water. So the incoming main is 20 degrees and we want to heat the desired temperature of hot water to 60 degrees. So that's 40 degrees heat energy required. So 1 litre requires 4.186 kilojoules to raise it by 1 degree. So the specific heat capacity of water is 4.186. So 1 litre of water requires 4.186 kilojoules to raise it by 1 degree. 2 litres, 8.372 kilojoules, 2 litres at 1 degree. To raise 5 litres of water by 1 degree, you're going to require 20.93 kilojoules. So to recap, specific heat capacity of water is 4.186 kilojoules, and that's the energy required to heat 1 litre of water by 1 degree. 5 litres, 20.93. 60 desired temperature. Take off 20, your actual temperature is 40. 4.186 kilojoules per 1 degree times 5 litres equals 100.9. So here we've got an incoming temperature of 20 degrees, desired target 55 degrees, specific heat capacity 4186, and we're heating 115 litres up. Here you go. DT, that's the temperature difference between the incoming temperature and the desired temperature. 35 times specific heat times litres equals 16,850. Let's look at relative density, which is mass over volume. Relative density, what does it mean? So here we have 4 items, 4 materials, and a cubic metre form. So we have a cubic metre of water, that is 1 kilogram. A cubic metre of ice weighs 0.92 kilogram. Cubic metre of lead, 1.34 kilogram. Cubic metre of copper, 8.9. What does that mean? Ice is lighter than water. So let's talk about water now. Water at 0, no change. When it goes to freezing, minus, it expands 10%. At 4 degrees, relative density, that is when it's most dense. From 50 degrees upwards, it expands 4%. When water turns to steam, it expands 1,600 times. That's because steam, the water molecules separate and they become further apart. So 50 degrees upwards, 4% expansion. That's why you have expansion vessels. So inside the expansion vessel, you have a diaphragm that'll move to allow for expansion. And you have feed and expansion systems always allow for water movement. 4% increase. Make sure it doesn't overflow. Water. That's when water passes through lime, stone, chalk. Hard water is calcium carbonate. Anything above 200 parts per million requires treatment. The only way, really, is a base exchange unit. Water goes in and comes out, and you put salts in, and they soften the water. You have magnetic descalers, electronic descalers, but the only way to actually treat it is a base exchange unit where you put salts in, often as iodolites. Temporary hard water is the dangerous water because when you boil the water, the calcium carbonates release and scale up. Now let's look at different types of heat transfer. Conduction, radiation, fluids, convection. Understanding plastics. So this is a plastic speed-fit pipe, polybutylene. Now, the good thing about this plastic is it can be heated up, not with a flame directly, with hot water or central heating water, and it can form a shape and go back to its original status. So whenever you're using plastic pipe, you have to take into consider expansion, like a gutter joint. Thermoplastic. And then you have another form of plastic that's called thermosetting. Thermosetting just melts. So there's two types of plastic, thermosetting and thermoplastic. One can handle warmth and heat, the other one just deteriorates. The other thing with plastic, it can't handle UV light or chemicals. So this plastic can't be used externally. Coefficient of linear expansion of guttering. A piece of guttering is 8 meters long, and the temperature difference is 30 degrees. So, temperature difference is 30. Length of guttering 8,000 millimeters. Times the coefficient 0.0018. Final calculation 30 times 8,000 times 0.00018 equals 21.6 mil. So here we have a gutter union. That is the maximum point where the gutter can slide into. And here we have the insertion line. And that is to allow for expansion. So the gutter goes in like so. For linear expansion in hot climates, the gutter can now move up can go in and back out again. Plastics. ABS. Solvent weld pipe. MDPE. That's your blue mains pipe. Poly butylene is speed fit. Let's talk about pH levels. Is it acidic or is there a lot of alkalinity in it? And let's talk about corrosion. Corrosion of metals. Is it caused by oxidization of water? Is it caused by galvanic action or electrolysis? pH paper results can give you a result of what is happening to the system water. And let's have a look. The pH scale. Neutral water is number 7. Acidic, that's naughty. If the water is acidic, bleach is 0.5. If the water in your heating system is acidic, then what that's going to do, that is going to help spread corrosion. That is going to spread ionisation of the small currents that promote corrosion between metals. If it's acidic, it's going to have cleanser in it, too much inhibitor in it. If the water is higher than 8.5, that's also bad. If it's a renewable system with glycolin and it's higher than 8.5, then that tells me the glycol is starting to deteriorate. And the glycol has turned into almost like a bacteria, and there's almost lumps of growth in there and oxygen. So above 8.5, that's also naughty. Also, if it's an aluminium heat exchanger, if it's above 8.5, that can actually cause some corrosion and deterioration on the aluminium heat exchanger. 7 is neutral. Between 7.5 and 8.5 is really what you want. And we'll have a recap in a moment. So now I want to talk to you about electrolysis or galvanic corrosion. And basically, you have two things. One called anode, which is a positive, and one called cathode, and that's a negative. So the cathode destroys the anode. The negative attacks the positive. They don't get on. And you have an electromotive series in metals, okay? So the positive is magnesium, and the negative is, say, copper. They don't get on. When they touch each other, there's no real issue. But what the problem is, when they get damp, small ions corrode each other. They create a circuit. So, for example, if you have copper and steel, it's fine. The moment you get damp between them both, they corrode each other. If you have a copper cylinder, it'll have a magnesium rod in, called a sacrificial anode. So all the negative ions from the cathode attack the anode. So let's recap. Anode, cathode. Positive, negative. Positive, anode, cathode, negative. The negative attacks the positive. Let's look into this in further detail. Using a DC battery in this experiment, we can see how the cathode destroys and deteriorates the anode, which is the positive. Understanding electrolysis or galvanic action. So basically it's ions that's passing corrosion ions from one metal to another, and it's the cathode destroying the anode. So here I've made a little bit of an exhaust. You've got steel pipe, brass, steel pipe, some aluminium. You've got some copper fittings. So this is a little bit of an exhauster made. Now then, this might last some time. This could be quite durable. Why? Because it's going to remain dry. If this had damp, water or moisture on it, then it would start corroding between the two metals that are at the opposite ends of the Electromotive series table. So here we have two metals, anode and a cathode. They both are fine, but the moment you add water or a damp atmosphere, the electrolysis galvanic corrosion begins. The anode and the cathode. The cathode starts to destroy the anode.
Greater the cathode
There's
area,
a greater area of the cathode,
anode,
so therefore the anode gets
will
destroyed
corrode.
quicker.
In our example, the
pH levels, so 7 is neutral. 8.5, the alkalinity goes so high it can be damage aluminium. As it goes high, it can mean bacteria, things like glycol. As it goes lower down, it becomes more acidic, and that's a positive for corrosion ions. Testing pH, you get the litmus paper, you put it in the water, and then you put the litmus paper to match up against the corresponding colour to get the number. So, galvanic action and electrolysis, how it works. So, here is the electrolysis or series table. The positive is the magnesium, and this is the anode. As we come down the chart, the copper is the cathode. The anode, the magnesium, is a positive, the cathode is a negative. So all the electrical ions attack the positive. So pH water, that's acidic, spread the ions more rapidly, aggressively, and about 25 degrees, it accelerates the corrosion, hence the term cold corrosion. So the cathode metals attack the anode, which is copper, and the magnesium. So the larger the cathode, the easier it will corrode the anode. The further apart the metals are along the electrolysis series, the more they will corrode. All you need is water to connect them both. Magnesium is also called a sacrificial anode inside a cylinder. So inside a cylinder, which is copper, you'll have a sacrificial anode, which is a magnesium rod. So all the negative ions attack the positive. Brass is copper and zinc. This can corrode and is called dezincification. Bronze is copper and tin. Gunmetal for stop taps is copper, tin and zinc. Alloys are 2 metals. Ferrous metals, which means they corrode, are magnetic. Pressures. One bar equals 10 meters head. Equals 0.2 bar. Gravitational pull towards Earth is 9.81. Here, from the overflow line to the base of the cylinder is 5 meters. So the pressure there is 49.05 newtons meter. So the answer is 49 kilonewton meter squared. So 1 kilonewton square equals 0.1 bar. Therefore, the answer is half a bar. To work out pressures, it's simple. Force divided by area equals Newton meter square.